Hello and welcome. We're going to be looking at a paradox today called St. Petersburg paradox. This is one of my favorite simple paradoxes that's just really fun to think about. It scratches my brain in just the right way. It gets me thinking slightly philosophically as well. It's pretty fun, so let's take a look at how it works. So it's a game that you play. All you do is you flip a fair coin and see how many coin flips in a row you can get. And the more coin flips in a row you get, the more money you're going to get paid out. So how does it work? Say I flip the coin and I get a tails. Well, tails is what ends the game. So in that case, I end the game and I just get a score of 1. Now, if I get a heads, that means the game goes on. So then, say next time I get a tails, now the game ends. In this case, I got a score of 2. And what is the reward for a score of 1? It's gonna be $2. What is the reward for a score of 2? It's gonna be $4. You'll see the pattern pretty soon. So if I get heads, tails, I'm gonna get $8 for that. Now, the general rule is that if I get n coins in a row, then I am going to get 2 to the power of n dollars from that. So the question is, and there's no end to it, right? There's no upper limit on how many coins I could potentially get in a row, at least in the mathematical, version, maybe not the real life version. So it just goes on forever and ever. So how much are you going to get on average from playing this game a single time? Let's see. So first of all, the probability of just getting tails immediately, that's going to be 1 and 2. Of getting 2 heads and then tails, well, it's 1 over 2 times 1 over 2, so that's going to be 1 and 4. 1 over 2 times 1 over 2 times 1 over 2, that's going to be 1 in 8. And 1 over 2 times itself n number of times, that's going to be 1 in 2 to the n. So every time I play this game, just from this possibility alone, I'm going to be getting $1 on average. Why? Well, it would be $2 if I actually got this outcome, but I'm only going to get this outcome 1 and 2 times, so I have to kind of weigh the $2 by the 1 over 2, so I'm multiplying here, and that's going to give me $1 on average from the game, just from this possibility alone. We still haven't looked at all the other possibilities. So from this one, on average, I'm going to be also getting I'm going to get $1 on average just from this possibilities. Because it's a bigger, if I do get it, I'm getting twice as much as if I get this one. But it only happens half as often as this one happens. So it kind of cancels out, right? I'm still just getting $1 on average from this possibility. And it goes like that all the way down. Even down here, I am getting $1 on average. And to get the expected value from playing the game, how much I'm going to make from it, I'm going to have to add up all of these dollars I'm getting on average. And what is 1 added to itself infinitely many times? Well, it's infinity. So on average, from this game, I'm going to get infinity dollars. That's my sort of expected value. Although you might technically say the expected value doesn't exist, but we get what's going on here, right? The expected value, the series, it is unbounded, and it is, in the usual sense, I'm not going to go over the limit definition and stuff. It's infinity. It's infinity! What's going on? Now say the price to pay the game, you have to, I don't know, spend $1,000 to play the game, right? Well, it's $1,000 to play the game, and you get an expected value of infinity dollars from the game. It's a pretty good deal, right? Let's think about this a little bit more. For example, if you spend $1,000 to play the game, what is the probability that you're going to make money from the game? Well, you would have to get at least 10 coins in a row. If you get 10 coins in a row, you're gonna get, $1,024. If you get 11 coins in a row, you'll get $2,048, and so on. So you're gonna have to get at least 10 in a row. Well, what's the probability of that? Well, getting 10 in a row is gonna be a probability of 2 to the negative 10. Getting 11 in a row is gonna be 2 to the negative 11. And then getting 12 in a row is gonna be that. And it goes on like this forever. And this all adds up to 2 to the negative 9, which means you have a 1 in 512 chance of making money from this game, and you have a 511 in 512 chance of losing money from playing this game. So it doesn't seem so appealing, although you do have to consider you could possibly make, I don't know, $1 trillion, you know, but hey, you could get $1 trillion. Or you could also get a grams, well, okay, technically you can't, you could get more than $1 trillion, or you could get more than a grams number of dollars, in which they'll have to try to encode the number in a machine to, and even then it's all gonna, like, the universe is gonna get sucked into this big money black hole. So let's think about it a little bit more philosophically, because let's say I have 2 rooms. Okay, there is the boring room on the left, and there is the fun room on the right. And the boring room, man, it's boring. There's just like nothing really to do in there. Now you could argue that you could just sit in there, close your eyes, and think about mathematics all day. And you've got me there. You've got a point there, but we'll just ignore that flaw with the argument. And then over here we have the fun room. This one is as boring as this one is fun, and you play the game. Let's say you have to spend grams number of days in the boring room just to play the game. If you don't know what grams number is, it's just a really, really, really big number. Okay, let's just say a Google days. Let's just be normal. So you have to spend a Google number of days in the boring room in order to play the game. And you're also, at the end of each day, you kind of get your memory wiped and then you start all over again. So you're not like panicking on the 10,000th day because you haven't been doing anything for 10,000 days. The 10,000th day is just like the first day, just a normal boring day, nothing crazy. And then you play the game, you get your reward. So say you get 20 coins in a row, then you're gonna get 2 to the power of 20 days in the fun room. So how well you do in the game determines how long you get to spend in the fun room. Now the question is, would you play this game? Think of it a little bit like this. Say I had, I don't know. I mean, would you play this game? Because the chances are you're just gonna spend a whole bunch of time in the boring room, and then you're gonna go to the fun room for like, you know, 2 days or 4 days, maybe 8 days, maybe something like 32 or 64 days. And it's not going to be even close to being worth it. But technically, the expected value, on average, you are going to get more than a Google number of days in the fun room. So is it worth it to take the risk, so to speak? I don't know. Maybe you'll get like over a grams number of days in the fun room, and it'll be super awesome. Let me know what you think, and if you have any questions as well. Thanks. Take care.